Hello friends, welcome to the channel of Digital to Real. Today I want to discuss about the topic of what is the need of verification methodology in system design or an asset. So there are many verification methodologies available which are based on system Verilog OOPS concept, just like OVM verification methodology, VMM verification methodology, UVM verification methodology. So they have a track record of verification success because as the design complexity has increased over the due course of time, advanced verification methodology was very much needed to find the bugs deep into the code, so that after silicon, when the design will go into actual chip, at that time it should be fault free. Verification methodology provide consistency and uniformity in the way the verification components are designed. As the verification components are library based one, so when the new verification engineer comes into a team or he replaces the old verification engineer, at that time he would not have much difficulty in understanding the code as it is well maintained and it is consistent with the methodology and it is very much uniform. The benefits of verification methodology: they improve the productivity. You can do the things fast if you know the methodology and the language of system Verilog. They enables or encourages the reuse. The same verification component can be used across projects. Every time you need not to change the verification component in order to make it suitable for a different project. So ease of use and reuse is there, and ease for maintenance. The randomization of stimulus in verification methodology helps to solve unforeseen limitation in the design code. So with the randomize function, we can randomize the config variables in the code, number of packets in the code, environment parameters and variables in the code. So in this way, we can make our test directed even with constraints. We can make our test directed and make it point to the specific bugs in the code. And even if we make the stimulus fully randomized, then we can even look for the unforeseen limitation in the code. Now what is OVM? So OVM is a proven open verification methodology for system Verilog. And it is jointly developed by Cadence URM based methodology, which is of class based, and Mentor's Avian methodology. OVM is used to deliver simulator and verification IPs which can be used within and across the companies. So they provide the licenses to the other company buy the licenses and make use of this verification IP. Because the verification component are reusable, they can be used at the system level verification. Means same verification component can be used at different level of the design code to verify. At the system level we can use, even at the low level for specific design features also we can test with the verification component. And this particular verification methodology, it is widely used semiconductor industry, and this methodology is developed, maintained, documented by multiple vendors. As per the requirement, different vendor make tweaks into the code and suit it for their specific project. Building a coverage driven verification environment. So the components of coverage driven verification environment are, so what is coverage driven? Means we will provide through the stimulus different set of inputs or drive different set of inputs to the DUT, and we will check at the output of the DUT whether the certain documented feature in the specification are being covered or not. So the coverage driven verification environment, that is what we build. And what are the components which are needed to build this coverage driven verification environment? Number one, automated stimulus generation. We have the provision of independent checking and coverage collection. Independent checking is that we are driving certain signals of the duty. On the output part, we are sampling the signals and we are checking whether they are matching with the input or not. Whether that means in the scoreboard we are checking that yes, they are matching their respective values or not. And the coverage collection, in order to make sure that what are the features which we have to test in the specification document, are they covered or not. So we collect them. Suppose there are 10 features to be collected. Okay, we see while sending the stimulus to the code, when the output comes out, only 8 are covered. So 2 are left to be covered. So 8 by 10. This is the percentage of coverage that has been done. So again, what we will do, we will randomize the stimulus. We will provide separate different seed in the stimulus. As a result, sending different seed for the randomization, we will get different set of inputs that would be driven into the code. Hence, in the output, we will find some different output. They might be covering some other percentage of the specification features. So this is how the coverage is collected. They are being checked, they are being collected. So this is how the coverage driven verification environment of a verification methodology looks like. So we have the test seeds. So these are some numbers we will provide. Depending upon the different stimulus will generate it. So automated generation of the test. We will have a test file, one program file, randomization of the config variable will be done, number of packets will be done, environment variable will be done. That all depends upon the seed passed. Okay. Through the randomization function, we are generating the automated generation of the test and automated generation of the stimulus also. So that would be automated test scenarios will be covered. Automated test will give automated test scenarios that would be sent to the stimulus generator. What the stimulus generator will do? After the test, after the generation, test will generate the packet, stimulus generator will send those packet to the duty interface. And from the interface, the monitor will observe what are the inputs which has been generated because of the particular seed of the test. Okay, and that would be covered by the coverage block. Here is the coverage USB. This is the duty. One side of the duty is the USB. Other side it is Ethernet. So USB signals will be sent and output will be Ethernet signals from the duty. And output signal that also will be observed by the monitor. This monitor will observe the Ethernet signals at the output side, and this monitor will observe the USB signals on the input side. So here one coverage collection, input coverage, what type of stimulus has been generated because of a particular seed, that would be collected in the coverage USB. Here is there another coverage collector. This will be covering what are the Ethernet configuration and signals have been generated. That would be covered in this coverage block. And this monitor, no, there is some scoreboard, some self-checking mechanism would be there. Okay, whether the outputs which are generated for the respective inputs are correct or not. That scoreboard will check. The self-checking mechanism, self-checking block would be there. So this is how the verification, coverage-driven verification environment look like. Okay. So if you like this video, please share with your friends. Please subscribe the channel and have a very nice day. Bye-bye.